If you want to upgrade the structural strength of anything you might be making, carbon fiber might be a good option. After all, it is one of the strongest materials for its weight that is available to use today. One of the ways that we can work with carbon fiber is to use a carbon fiber winding machine. This basically takes a spindle of carbon fiber and winds it around a mandrel in order to create a 3D structure. This can be really useful to make structural tubes or other cylindrical structures like tanks. But if you're not really familiar with carbon fiber winding, it may be a little bit daunting to be standing in front of a carbon fiber winding machine wondering, how exactly does this thing work? Today I'm going to introduce the important concepts that you'll need in order to use the carbon fiber winding machine. If you're into carbon fiber winding, you may have seen lots of videos of people winding these beautiful carbon fiber tanks or structures using their carbon fiber winding machine. But how do you make that a reality for yourself? I'm the chief engineer at a group called ASTRA, and we're specifically using carbon fiber in order to make our tanks that we're going to use for our rocket, which will hopefully make it all the way to space.
Have you tried turning it off and on again?
Carbon fiber winding machines will have 4 different axes in which they can move. The first is the x-axis, which is basically just moving the spindle back and forth down the length of the tube, and we call this axis the x-axis. The next axis is the y-axis, which is the rotation of the mandrel. Then we have the z-axis, which is the movement of the spindle forward and backward from the tube itself. And then finally, we have sometimes the case where you can actually rotate the spindle. This is helpful for when you're winding things and you're going like around the end of a tank. But for winding just a tube, this isn't usually used. But this is usually called the a-axis. So you're just rotating that spindle around itself. When we want to use the carbon fiber winding machine, we're basically going to manipulate these 4 axes in order to generate some sort of 3-dimensional shape on the mandrel that we're winding onto.
That's a nice triangle.
Carbon fiber really only has strength in one direction, which is the length that the fibers are orientated, and it has pretty much no strength in any other direction. So you have to layer the fibers in all these different orientations to give you strength in all directions. So let's say that we have a part that you want to wind that is 1 meter long. And because this is going to be used for a tank, you want to actually wind at 54 degrees. This happens to be the best angle to wrap at if you want to make a tank, because it gives you twice as much strength in the radial direction as it does in the axial direction, which is also the distribution of forces that happen on a tank. How do we get to have this perfect angle of 54 degrees when we're wrapping down the length of the tube? Now, to do this, we have to think about what is happening with the spindle and the mandrel as they're rotating and moving. When we wrap this angle of 54 degrees, we actually want the spindle to move down the x-axis whilst the mandrel rotates around the y-axis. Now, if you imagine that we take that mandrel and we roll it out so it's in fact a plane, what this ends up creating is a triangle where we can have one leg of the triangle be the x-axis, which is the movement of the spindle down the length of the tube. The other leg of the triangle is the y-axis, which is of course the flattened out version of the cylinder. And this is just a right triangle, which has an angle on this foot here, which is equal to theta. Now, assuming that you know the length of your tube, in this case, it's being 1 meter long, so x equals 1,000 millimeters. You know what theta is, it's equal to 54 degrees. So now you can figure out what y should be in order to give you the degree of 54 degrees that you're going to wrap at. And to figure that out, you just have to do some trigonometry. You'll discover that y should be equal to x times the tan of theta. And in this example, we'll discover that y is just going to equal to, so it's just going to equal 1,376.4 millimeters. Now, typically the y-axis is not represented by millimeters because depending on the radius of the tube that you actually put onto the winding machine, that will be different. Because if you have a really big radius, then that means not so many turns. But if you have a really small radius, it means lots and lots and lots of turns. And the machine needs to know how many times do I turn it for how much distance you move in x. So we have to convert the y-axis into degrees. We basically have to take the y-axis triangle direction. We have to divide that by 2 pi r, which is the circumference of the tube. And then we just have to multiply by 360. The number of degrees in one first cycle. And that should convert our y-axis direction into a degree. Now in this case, let's imagine that we have a tube with a radius of 100 millimeters, and then we can just basically plug into this formula and figure out what our y for the G code should be. And the G code is just going to be the machine language that we're going to send to the computer in order to tell it how to basically control the spinning of our part. And that gives us a total degree that we want to spin the y-axis of 789. So armed with this knowledge, we should be able to generate a perfect 54-degree wrap angle. G code is usually pretty simple. We just have to tell each axis how to move. So if we imagine our tube again, right now we just want to tell the spindle to, if it starts here, we want to tell it to move down the length of the tube to the other side. So to program it to do that, we just have to say, okay, x equals 1000, which is the length of the tube that we wound down. Y will be the 789 degrees that we calculated. Z will of course be 0 because we're not going to move the spindle back and forth. And A of course will also be 0 because we're not dealing with any rotation of the spindle. But now that we're at one end of the tube, we have to of course get back to the other end of the tube. So we just have to basically reverse the spindle and go backwards to the start point. So X will be minus 1000, Y will stay 789, Z will be 0, A will be 0. But this isn't quite the whole story, because now we have to think about the pattern that we want to generate. In the case where we just move the mandrel back and forth, what will end up happening is that we'll actually be in a situation where if you imagine the fiber being paid out behind the spindle, the fiber will kind of make an angle to the tube. And so when we get to this point here, essentially the fiber hasn't really gotten to the end yet. And so if we immediately start going back, like we programmed the computer to do here, this fiber here won't actually get to the end of the tube. And we'll end up kind of missing the ends of the tube, and we won't get a full 1 meter length tube. This may be undesirable. So we have to consider also a turnaround period. And when we consider this turnaround period, we have to also consider the pattern that we want to actually end up winding. So if you imagine, we might end up winding a pattern that kind of looks like this. And then when it comes backwards, it'll look something like this. And then we want to actually have the next fiber come down right beside the previous one. But to achieve this, we need to think about the amount of the rotation that we're having the mandrel go through so that we can achieve the placement of the fiber in the exact same spot that we started at, except just offset by a couple of degrees. And the way that we control that is by thinking about this turnaround period and programming that properly so that we can achieve the right ratios that we want to have. Based on ASTRA's experience, I think that a turnaround period that is greater than 180 degrees, but less than 360 degrees, kind of the desirable range that you want to kind of sit in. If you're less than 180 degrees, typically the fiber won't really have enough time to actually do a proper turnaround, and it won't really make it to the end of the mandrel. On the reverse end, if you have more than 360 degrees, you'll get kind of bulging on the ends because you'll be really winding a lot of fiber over top of itself on each pass. So you have to kind of balance those two things. But now we get to the interesting part, which is how do we make sure that we have a proper repeating pattern. So to do this, you have to account for all of the movements that the spindle is making through one cycle of movement. So for moving forwards from the start to the end, you can think about that as phase 1. And then the first turnaround, you can think about as phase 2. And then when the mandrel comes back, you can think of that as phase 3. And then when it does a turnaround at the start point, you can think of that as phase 4. So there's kind of like 4 phases to this whole part. Now we've understood phases 1 and 3 already by just moving the mandrel forward and then backwards. We just need to figure out what phases 2 and 4 are. So to do this, you kind of want to find what your y total is. And that's just going to be equal to y1 plus y2 plus y3 plus y4. Now, if we want to make a balanced tube, y2 should equal y4. So we can kind of just simplify what's happening here to just y total should equal 2 times y1 plus 2 times y2. And of course, we already know what y1 is, which is 789. And we want y total to be something that is a proportion of 360 plus or minus a couple of degrees. So let's think about what a perfect world is. If we take our 789, multiply it by 2, we get 2y1 is equal to 1578 degrees. Now you want to think about what the closest multiple of 360 degrees is to 1578 degrees. So if you just divide that by 360, you'll notice that equals 4.38. That means that you could either choose something like 5 or 6 cycles in order to have a repeating pattern. So if you choose something like 5 cycles, all you have to do is just take 5, multiply that by 360, and you want your y total to be 1800. So let's say y total is going to be 1800. Then you just have to basically solve to figure out what y2 should be. Again, this is just some simple algebra. So if you do the algebra, you'll figure out that y2 equals 111. That's not quite in our range that we want our turnaround to be. Like we said, we want our turnaround to be between 180 and 360 degrees. This is giving us a repeat of 5 cycles, but maybe we can have a repeat of 6 cycles instead. All we have to do is just add 180 degrees to each of the turnarounds. So if we take this number and add 180, we'll end up at a better y2 turnaround of 291 degrees. And theoretically, this should give us 6 cycle repeat patterns. Of course, if you use 291, you'll end up winding a perfect 5 cycle pattern where you'll end up with fiber exactly on top of where you were for the first cycle, and you won't be winding a tank then, you'll just be winding a really strong helix. So if you want to have a pattern where you have the fiber landing just beside the previous fiber, what you want to do is either increase or reduce the turnaround time by a couple of degrees. But what amount is going to give you the result of the best pattern? That's a good question. You're going to have a situation where you have like a fiber coming here and a fiber coming here. Now we want to make sure that we have full coverage across the entire length of this tube. We want to have fibers coming like right beside all the way down the length of the tube like this, right? So we basically just want to have one layer. So we want to make sure that the width of each of these layers is the amount of distance that we want the next fiber to lay beside, right? That we have full and complete coverage. So first we have to figure out how long this distance actually is. So when y rotates 360 degrees, how far do we move in x? That's the question we want to solve. And again, you can just think back to your triangle, right? X is some value, y is 360 degrees, and you have our angle, of course, being 54 degrees, which is theta. So to find the y part of it, of course, all you have to do is just take the circumference of your tube. So in this case, it's just going to be 2 times 3.14 times 100. So we know that y equals 628 millimeters. And then again, you can just use trigonometry to figure out what your x is going to be. And in this case, x is just going to equal your y divided by tan of theta. X is just going to be 456 millimeters. So if we want to cover 456 millimeters, and let's say that we're having a fiber that's about 10 millimeters in diameter, then we know that we're going to need at least 46 repeats, like 46 fiber cycles, in order to cover one length of that distance. Now, in order to figure out how many degrees we want the cycle to repeat so that it comes right beside the next fiber, we just have to take that 46 times, have 360 divided by that. In this case, it's going to be 7.82. And that's how many degrees we want to have extra or less than a perfect cycle, such that our fiber will land exactly beside the next fiber. We had said that we wanted to have 291 for our turnaround time, and that would give us a perfect 6 cycle repeat pattern. All we have to do is just take the amount of degree that we want to offset, which in this case is 7.82 degrees, divide that by 2, and then add or subtract that to the turnaround. In this case, I'm just going to add that to the turnaround. So you take that 291 plus 7.82 divided by 2. And of course, that's just going to give us 294.9, which we can kind of just round up to 295. So that'll give us a really nice repeating pattern that should hopefully wind us a really nice tank. So finally, you want to put all this together and you want to write some G code that's going to describe all of this. Like we had before, we're going to have the X move 1000, Y is going to move 789, Z is going to be 0, A is going to be 0. That takes us all the way down to here. Then we want to program our turnaround. There, X is not going to move, so X will be 0. Y will be the defined 295 that we had before. That's just a turnaround. Z will be 0, A will be 0. Then we want to move the manual back, so the X is going to be negative 1000. Our Y will still be the 789. Z will be 0, A will be 0. And then finally we want to execute that turnaround on the start point as well, and that'll take us back to the starting point of the entire cycle. So again, X will be 0, Y will be 295, Z will be 0, A will be 0. And this represents the code that you'll need to do one single cycle of your winding process. Of course, if you want to wind an entire tank, you'll need to do many repeat cycles of this. And in our case, because we calculated that we're going to need 46 repeats to have full coverage of a length, that means that we're going to actually have to repeat this cycle 46 times in order to get one full coverage of the tank. And this will give us one layer going this way, and of course also one layer that goes backwards as well. So in the essence, you have one 54-degree angle and one negative 54-degree angle. And then yeah, you just do multiples of 46 for each of the layers to build up your layers further and further and further. And then you can wind a nice, beautiful carbon fiber reinforced tank. We hope that you were able to learn a little bit along with us, and I'm looking forward to seeing some of the things that you make with your carbon fiber winding machine. And remember to expand your horizons.